So we're going to do the blood vessels. Is that anything that carries blood away from the heart is an artery until it's not. I'll get to that in a minute. But sometimes from the right side of the heart it's carrying deoxygenated blood. Sometimes from the left side of the heart it's carrying oxygenated blood. But this is you're taking the blood out to where it's going to be distributing stuff, right? Your blood's carrying things. It's got oxygen, got nutrients, got, well, hormones. The hormones in the circulation work a little bit weirder because you never know where they're going to get picked up and where they're going to be settled down. But oxygen and nutrients going out to the cells that need them. And the first thing you do is you stick them on the highways to get them there. You don't unload your truck from the highway, from the throughway. You have to get it out to the surface roads. And your throughway is your arteries. Arteries are structurally different from the other vessels. They are thicker around. The inner epithelium is kind of convoluted because they need to be able to expand, and so the inner epithelium needs to be able to kind of stretch. And they are flexible. We talked about how as you get older and you lose the flexibility of the collagen, that your arteries get stiffer, they get hardened. And when a pulse of blood, a push of blood expands the arteries, its automatic reaction is to squeeze back and help push it even farther. So your arteries are secondary pumping stations. They help the blood to get out to where it's going. Blood pressure. That is the push of the blood and also the background pressure that's there all the time. So how do you read the blood pressure? You roll your sleeve up, they put the cuff here, they listen there, and they take the little pumpy thing and they pump the cuff up. It fills the cuff with blood, with air, and it exerts pressure on this artery going out your arm. What you want to do is squeeze that artery shut. So you put lots and lots of pressure, and you can listen. You get up high enough, it's going to shut the artery. But you listen because you can hear the blood kind of squirting through if the blood is squirting through. So you pump it up, pump it up, pump it up. And then you slowly relax the pressure, and you listen for the blood. You can see it on the gauge also. When I used to teach anatomy and physiology, I could look over somebody's shoulder and read the gauge as well as they can, listening to the sounds of Korotkoff, which is what they're listening to with the stethoscope. But what happens is, on the old gauges that actually had a needle on them, you'd see they'd pump it and the needle go up and the needle go up and the needle go up, and then they'd put their stethoscope on and relax the pressure. And the pressure would come down and come down and come down. And then it would hit a point where the blood had enough pressure to squeeze through a little bit. So it would push back on the cuff, and the cuff would start to drop this way. So it would, the blood pressure would push and keep it from dropping evenly, and push and keep it from dropping evenly. And then eventually, it would hit the point where it wasn't really squeezing the artery shut at all. So there was no pushback, and it just drops smoothly. So it starts smooth, it jumps for a bit. That upper place where it starts to jump is your systolic pressure, and then eventually it hit a point where it drops smoothly again, and that's your diastolic pressure. Your systolic pressure is the push pressure. Your systolic or your diastolic pressure is the pressure that's always there, your baseline pressure. And if you have high blood pressure, typically they think The problem is more with your diastolic pressure, the pressure that's always pushing on these blood vessels is the one that you really don't want to be super high. And the nurses learn, if you want to know which one is which, it's sky over dirt. But that's basically how the blood pressure cuffs work, is that they've got them on your wrist. The wrist ones work okay. They've tried other places where you can get a reading off of the pressing and releasing, but this one works pretty doggone well. We also talked about as you get older, you build up deposits on the inside of your arteries. It's like water going around a stream bend, is that material that's being carried by the quick flowing water, the water kind of bends, hits the end of the bend, it kind of turbulent, comes into the inside of that curve, and it slows down because it's doing this on the inside of the curve, and it tends to drop stuff. And so if you have a big bend in a stream, on the inside of that bend there'll be sand, there'll be a sandy bottom, because the sand's been carried in the water, as long as it's going fast. When it goes slow, it settles. The lipid material in your blood that you're trying to get out so that you can make cell membranes and other sorts of stuff that's being carried by your lipoprotein carriers, it doesn't really dissolve. It's kind of suspended in the fast-flowing liquid. And it also will settle down on the inside of a curve and stick to the inside lining of the artery and build up there. And we talked about how clotting will the turbulence will produce a clotting response that'll smooth that over. But now you've got a smoothed over deposit on the inside of the curve. Then you get more deposits on top of that, and you smooth that over, and it gets so that the run through of the blood gets narrower and narrower and narrower as the deposit on the inside of the curve gets built up and built up and built up. But this happens primarily in arteries because that's where the fastest flowing blood is. And it can be in arteries coming out of your heart. It can be a lot of times in the coronary arteries in your heart, because that's coming right out of your left ventricle. It's being pushed very forcefully. So turbulence on the inside of the curves is very much there. But it also can happen to the arteries going up into your brain. Is one of the major offshoots of this major artery, your aorta, your two carotid arteries go right up into your brain. So there's a lot of force there pushing blood around corners. And your blood vessels in your brain can also squeeze shut. And the smooth muscle, if something, stress or exercise or something causes the smooth muscle to tighten up, it can squeeze those tight places shut and cut the blood flow off to your heart muscle, to your brain. Heart muscle produce a heart attack, to your brain produce a stroke. So the blockages are pretty bad. So the arteries branch and branch and branch and branch because they got to run blood all over the place. When it gets small enough, they're called arterioles. Arterioles are essentially built like arteries, so we're not going to really differentiate. But eventually, you need to be able to get stuff from your blood to your cells. And arteries are bad for that because they have this thick lining, smooth muscle in a way. So the nature of the blood vessels changes, and they get very small. They are literally a series of ring-shaped cells stuck to one another. Pretty tight, pretty small opening inside. And as I've mentioned, the connection between the cells isn't always that tight. So stuff can leak out in between these ring-shaped cells in the capillary linings. So this is for your distribution. This is for moving stuff from your blood into your tissues and from your tissues into your blood. Because you got to pick up waste materials too and take them for disposal. So it's not just stuff coming out, it's also stuff going in. Carbon dioxide absorbed into your plasma, waste materials, protein breakdown waste materials, urea, and other similar molecules being absorbed into your plasma to be gotten rid of in your kidneys. So the distribution and the collection. A lot of the distribution I mentioned is not through the lining of the capillaries, it's through the gaps. So there's a bunch of nutrients and stuff that don't go through membranes that easily. So rather than make it have to go through the capillary membranes and then through your cell membranes, it just leaks out with the fluid. But that fluid has to be collected into your lymph system. Then the lymph has to be brought back up. It's eventually, the fluid is dumped back into your heart, the way blood cells dump back into your blood. Your capillaries are not the same everywhere. People that are designing drugs that go into your circulation and then do something in your body, most of the places those drug molecules come out with the leaks, right? They come out in the fluid that comes out through the gaps. The capillaries in your brain don't have the leaks, is that they're very tightly zipped together. And the only way for stuff to get out into your brain is for it to go through the membranes of the blood vessels. Same for stuff going back into the blood. So there's a lot more pumping and moving of stuff through your blood-brain barrier. But that's a problem if you're designing a drug that's supposed to act on the brain or spinal cord. Getting it into the blood isn't enough. You've got to be able to get it through the blood-brain barrier. Or you need to inject it directly into spinal fluid, which is a big deal and not, optimum. But you got to get it through the blood-brain barrier. Whereas why the blood-brain barrier is there is not entirely clear. Because if you've got pathogens in your circulation, you got a problem whether it gets into your brain or not. So yeah, you could say it's harder for pathogens to leak out through the gaps into your tissue fluid, but your immune system should have taken care of them anyway. So there are some things that can survive your circulation for a while. So you've done your distribution, you've done your collecting, you got to get the blood back to the pump. And so the capillaries get bigger, the branches start to merge, and now you've got venules and eventually veins. Venules are just little bitty veins. Now the blood has lost almost all of its pressure. It's got a very slight push behind it, but the pressure has been, because a lot of fluid's been lost and there's been a lot of splitting into little bitty tubes, both of those will drop the pressure pretty considerably. So veins are not a high pressure system. There are ways to take the pressure in veins. There's some conditions where you need to do that, but it's tricky and it doesn't really tell you much for a lot of things. But veins are, because they're not resisting pressure, are thin. They don't really get pushed open and shut. They don't have pulses, so they don't have to be flexible. And with the exception of a discovery a couple of years ago of occasional veins with smooth muscle, no matter what the rules are, somebody's going to find an exception. Your veins don't typically have any kind of muscle lining in them. What they do have, there we go. Where do I have this? Is they have anti-backflow valves. So the blood being pushed just pushes its way through the valve just opens up. And if something stalls the blood and it tries to push back, it just closes the valve down. Why? Because there isn't a lot of push. And sometimes you got to get the blood back up from your feet, and that doesn't have a lot of push behind it. What generally happens is the veins are routed through areas that can tighten. In this case, they're showing muscle. And so just standing in one place, actually, your muscles contract enough to hold you up that the veins that are going through your muscles get squeezed. And the blood can only go one way because of the valves. The veins that come out under your skin, because when you move, it tends to tighten the surface of your skin, they also get squeezed, but they don't get squeezed as well. So if you're in a job where you are standing in one place all the time, you're not really doing a lot of movement, you're not really tightening that skin layer, those veins start to pool up blood, and that starts to stretch them. They also have more room to stretch because they're in connective tissue under your skin. There's not a lot holding them there, as opposed to the ones that are routing through your muscles that are pushing against muscle to expand. What I'm talking about are varicose veins. Varicose veins are, you see these spider veins under somebody's skin because the veins have stretched out enough to be visible and the circulation is compromised. The first thing that they do is they put people in stockings that squeeze, that help to add to the squeeze on the veins to help get the blood back up. But in extreme cases, what they'll do is they'll go into your ankles and they'll actually seal off the veins that come up under your skin. So the blood has to come up through your muscles and therefore it'll be pushed. There's a similar thing going on with hemorrhoids where veins around the anal sphincter and the rectum in general expand. Sometimes they expand right up onto the surface. Sometimes they kind of bump up out of the surface. They cause enough insult to the tissues that it causes itching, sometimes pain. And hemorrhoid creams are blood vessel shrinkers, so they help to shrink the veins. And again, in extreme cases, they go in and they literally seal those veins off with the old surgical live soldering gun. They seal the veins off and make the blood go some other way rather than through that area. Since your veins are somewhat thin, impact can crack your veins open and cause leakage of blood under the skin. That's what a bruise is. As you get older and you lose collagen, your veins are thinner and they're more prone to damage. You're more likely to bruise. And the bruise is that eventually you take all that leaked out skin or leaked out blood, and of course it's clotting while it's spreading. So the size of the bruise is also an indication of how well your clotting system works. My sister has clotting issues, so she used to get bruises really easy, and she'd get huge bruises. And the change in color is because your body eventually breaks down and reabsorbs those chemicals, but it does it in a particular order. So eventually the chemicals, well, most of what's left is kind of greenish. The other organs that are associated with your circulation we will deal with later. We've talked already a bit about your liver in terms of it produces blood cells. It's a storage place like your spleen for white blood cells. That's why those kids in third world countries that have these huge bellies, people go, oh, that's malnutrition. No, it's not, it's parasites. It's that big repository of white blood cells on both sides of the belly that make you have a big belly because you're being exposed to a lot of parasitic invasions and you need lots and lots of active white blood cells working. And we'll talk about the removal of waste in the kidneys, but that'll be other systems.